direction of modeling real physical systems. In that, there are actually various approaches to this sort of modeling. The probe brain approach that I'm talking about here is called top-down sometimes, because one actually constructs a fairly concrete model of something. There's another approach called bottom-up, where you simply start with Einstein's equations plus some other equations on three-dimensional or four-dimensional, typically four-dimensional space-time with a cosmological constant that will give you asymptotically anti-de Sitter space, and try to look for phenomena there by solving the equations with various boundary conditions. That has the advantage that, well, it's a little bit easier, quite a bit richer in some ways. It has a disadvantage that you don't really know what the dual field theory is most of the time, maybe not even any of the time. So the dual field theory is a little bit obscure. Being richer, it does have perhaps a better chance of finding sort of universal phenomena. After all, it is really just one approach with one set of equations. So the best you're going to do with it really is to find some phenomena that happen in any strongly coupled system, maybe with some assumptions. Say any strongly coupled system where perhaps hydrodynamics is good or something like that. And there are some examples. Now, in the top-down approach that I was talking about and will continue talking about here, it's a little different in that one can be a little more specific since you know what the model was. And I'd like to continue the D5 brain and talk about it some more. Of course, there are a lot of other probe brain theories. I noticed one of you during the Gong show was talking about a D7 probe brain system. That's also very interesting. That's a space-filling probe brain, so it modifies n equals 4 by adding extra stuff. So that has its own interesting features. I'm not going to talk about it here, mainly because, well, I've worked on it less, and I'm less of an expert on D7 brains. At least those kind. D5 brains also, to my mind, have some very interesting features in that, number one, they're quite well studied. They're nice, stable models, which, and in some sense, they're the only ones that are really tested, where the duality is tested at all. And they have a rather nice story to them, which I sort of began telling you last time. Okay, so that story went something like this. If we take our anti-de Sitter space, which should be wider at the top than the bottom, I'm just not a good artist, and put in our D5 brain, and then we want to study this holographically by deforming it in some way. So this thing, the absolutely symmetric solution, is dual to a defect CFT. So if I draw a four-dimensional space-time as this box, it's something with a defect cutting it in half. Inside the bulk of four-dimensional space-time is n equals 4 super Yang-Mills. And then there's a field theory that lives only on the defect. And that field theory has chiral, some chiral hypermultiplets that whose number is equal to the number of probe D5 branes one puts. So one could put more than one, and typically put a stack of them on top of each other. The defect field theory is actually fairly simple in field content, although the full interacting Lagrangian is a big mess, which I'm probably not ever going to write out for you. So it has some scalar fields and it has some spinor fields. And it has some interactions between them, and interactions between them and the bulk fields, both the scalar fields and the gauge fields and the fermions in the bulk and so on. But this is actually integrated over the defect, so there are operators here that integrate the bulk fields on the defect. Now from the bulk fields, trying to remember if there are actually symmetric marginal operators which fit on the defect. You have to construct dimension 3 operators that obey all the symmetries. I'm not sure that there are any, but not really sure because, of course, with the fermions, there might be things. But coupling of the defect fields to the bulk fields, there certainly are things. For example, even this covariant derivative can contain the bulk gauge field. Okay. So this is a defect field theory. So what I discussed last time is you want to now study this by deforming it in various ways. Introducing external fields, charge density, temperature. So temperature I will say very little about, but it is something that's easy to do, and many of the people who work in this field insist, in fact, that it has to be done. They think of the zero temperature limit as being a little bit singular somehow. I tend to like zero temperature just because it's a little less complicated and a little close to something one can deal with analytically. So I'm going to stick with zero temperature. The way they go to finite temperature is instead of this anti-de Sitter space that's embedded in, they introduce the anti-de Sitter black hole, the ADS5 black hole solution. And then the temperature is just the Hawking temperature of the black hole. The picture looks a little bit like this. Of course, it's not as symmetric because the black hole doesn't have the scale symmetry except asymptotically at infinity. And the bottom here would be the event horizon of the black hole rather than the ADS horizon. Okay, so that's how they go to temperature, and I will not do that here, just to keep things simple. And that's because the phenomena I want to look at aren't really temperature dependent. The other ways in which we deform are with a magnetic field, like last time, and with a charge density. And both this magnetic field and the charge density live in the U1 symmetry of this defect theory. So this is not a symmetry of the bulk. It doesn't come from n equals 4. So the magnetic field and charge density doesn't couple directly to the n equals 4 fields in the bulk. There's something extra. They actually come from the U1 symmetries here. So they live on the defect entirely. And so the U1 charge density would simply be a density for the nether charge corresponding to the U1 symmetry of this field theory. And actually, if there are a number of D5 branes, that U1 symmetry is promoted to a U of N5 symmetry. I will never make use of the UN5 symmetry here. But really there should be such a symmetry, and there could be interesting questions about it, like spontaneous breaking of the UN symmetry. I never really make use of that. I will never, well, Maybe a little bit, but I would say that's a fairly unexplored direction in this sort of holography. If you really have non-abelian configurations of the gauge fields. So I will not go there, and I would say understanding that a little bit better is right now a research problem. Okay, so I told you last time what happened when you turn on the magnetic field. It's useful for that to have another picture of the 5-sphere over here. So here's my depiction of the 5-sphere. This D5 brane, well, this is really a 4-dimensional space, right? This slice of ADS5 is really just an ADS4. So it needs 2 more dimensions, and those dimensions sit on the 5-sphere. They sit in a 2-sphere that sits at a pole of the 5-sphere. So this one down here is S5. This one up here is S2. And this configuration, the one that's symmetric and stable, is one that really sits at a pole up here and is as big as it can be. So I haven't drawn it as big as it can be. It should be a 2-sphere that just fits exactly in the 5-sphere. The radius of the 2-sphere is the same as the radius of the 5-sphere. I probably wrote for you the equations. If you think of the 5-sphere as a unit sphere in 6 dimensions, 6 Cartesian dimensions, then this 2-sphere in those 6 dimensions would have this equation. Right? It would be as big a 2-sphere as you could embed in the 5-sphere. And I take that as sitting at a pole for some reason. That seems to be the convention. Now, if it moves away from the pole, here, I think of it as getting smaller. That means its radius should get smaller, and some of these other x's should become non-zero. That, of course, breaks a symmetry here, because you have to decide which of these x's become non-zero. It picks out a direction in this other space. That actually breaks an SU2R symmetry of the supersymmetric field theory on this side. And that SU2R symmetry is a symmetry under which the spinor transforms like a doublet, like a spinor. So there's SO3R symmetry, which this guy transforms under, which is simply the direction you would go away from the North Pole of the 5-sphere. The SO3 symmetry of this 2-sphere, the scalar field, is actually a doublet. So I call that SO3 tilde. And the geometry there actually has this SO3 cross SO3 symmetry, which is inherited from the original SO6. Right? So introducing this 5 brane breaks the SO6 symmetry of the n equals 4 theory down to SO3 cross SO3. And this object is ADS4 at this point. Okay. So the field theory dual of this configuration is pretty well understood. And one might conjecture something like one conjectures for the n equals 4 ADS5 duality, that it's really good for all values of the coupling constant and all values of n and so on. We find it at large n and the geometric side at strong coupling in a sense, but you might make a conjecture that its validity is bigger than that That conjecture is largely untested. It's an interesting one. Certainly, certainly a non-trivial generalization of the usual ADS-CFT duality. Okay. So I told you before, when you put a magnetic field here, so that the magnetic field here looks like this, it's just perpendicular to the defect. Right? In two space dimensions, a magnetic field is actually a scalar field. Well, maybe a pseudoscalar field. Right? In 3 plus 1, it's a vector, so that means the relevant component is perpendicular, that vector is perpendicular to the defect. As soon as you do that, on this side, well, on this side, how do you do it? Actually, you just put a constant magnetic field for the world volume gauge field of the defect. It turns out that at the boundary goes to a magnetic field on the boundary theory. In a sense, it sources a magnetic field on the boundary theory. What happens to the defect? Well, one should reanalyze whether this is really a minimum of the energy. So I'll show you how to do that in a few moments. But what happens is that it no longer is. In fact, the minimum of the energy always has a defect truncated somehow, stopping before it gets to the horizon. So pinching off, so to speak. And it pinches off like the cigar, sort of famously. Let me draw the cigar here. So the cigar has a tip. I guess the smoke comes out this end and the fire is at this end. And the way it pinches off is you can think of a circle around here, an S1 cycle, which shrinks to 0 size as you come to the end, and that's what allows it to pinch off in a smooth way. Right? There's no singularity at the end that the smoke comes out of. And so the same thing happens here. This D5 brane pinches off, and the cycle that shrinks is actually this one. So this guy moves away from the top of the sphere, breaks the SO3 symmetry that was at that point, and it shrinks, and when it comes to the bottom of the brane, it shrinks down to a point. And that's the shrinking cycle that allows this geometry to cap off in a smooth way. Okay, so, and that is a solution which minimizes the energy when a magnetic field is turned on. And the equations that determine the geometry actually have the symmetric solution and the non-symmetric one, and they compete with each other, but the magnetic field one always wins the competition for any value of the field. And I guess one can understand that if it's going to win the competition at all, it doesn't really matter what the magnitude of the field is, because it's stuck into this geometry which is otherwise scale invariant. So as long as it's non-zero, there's no real difference in what the magnitude is at this point. And I described to you last time what that means in terms of symmetry breaking here, and in fact how that is an extrapolation of what you can see happening at weak coupling. One can sort of understand what happens at weak coupling. All right, now I want to discuss what happens when you put an electric field, and I'll do it in pictures, and then I'll do these things in formulas. But it's good to understand in pictures what's happening first of all. So an electric field, what I mean is a charge density. So I want a charge density, uniform charge density living on this brane. And the charge density, like I've already said, is just the U1 charge, the nether charge corresponding to the U1 symmetry of this action. And even if there's a whole bunch of D branes, I still just use the U1. The U1 subset of UN and N5. Okay. So I want a charge density here. Over here, what that corresponds to is an electric field. So I might have B here. An electric field on the brane world volume in the radial direction. And the flux of that electric field through the surface at infinity is what gives the charge density. And that electric field can't be constant. It has to depend on R just to solve Maxwell's equations. But indeed, the electric flux lines have to go in the radial direction, and they can't disappear. It means as soon as I have an electric field, this D brane, even if it isn't symmetric, is forced to come down to the horizon. Because the electric lines of electric flux have to go somewhere, and the only place for them to go is into the ADS horizon. So you can immediately say something geometrically. You turned on an electric field, the charge gap that you had with just a magnetic field has to go away again. So even in a magnetic field, it's ungapped. What does that mean in terms of pictures? Well, we had a weak coupling picture of this, where in a magnetic field, right, you had Landau levels, and the symmetry breaking you sort of had a picture of, and you had a condensate psi bar psi. Once you have a condensate, the energy spectrum of the fermions, say, looks something like this. I'm not worried about the bosons yet, just the fermions. I've given you an argument why they are the important things at very low energies. Okay, so you turn on a magnetic field, there's a mass condensate. So in some way the fermion looks like it's massive. The neutral state with the magnetic field had all of these guys filled up. Now if I turn on a charge density, I should fill some levels up here, or empty some down here, but let's say I fill them up here, like that. That gives me a charge density. This is now, yet again, an ungapped system. Before these were here, to excite something from just this stuff full, you'd have to excite something across the gap. So that was the gap at the bottom of the brane. Now when we put a charge density, you fill up these guys, and there's no gap anymore. Right? Again, to excite something, you can just go a little bit above the Fermi level there. And that's seen qualitatively by the world volume of this D brane being forced down, back down to the horizon by the fact that there are these lines of electric flux threading through it that would otherwise have nowhere to go. They can't just end in a non-singular way. That actually brings up another question, which goes back to the weak coupling discussion we had last time. So let me just ask that question before I go on to something a little more technical. So with zero charge density, before symmetry breaking, it said if you turn on a magnetic field, the spectrum of the particles here is split up into Landau levels. And in 2 + 1 dimension, they're completely non-dispersive, right? In 3-dimensional Landau level still has a wave number in the perpendicular direction along the magnetic flux lines. In 2 dimensions, they're not. It's simply completely discretized. And so the energy states of the fermions look something like this. There were zero modes and then non-zero modes. And actually they go like a square root. They're not evenly spaced like I tend to draw. Just I don't know how to scale the distance between my lines as a square root. They get closer together as you come down here. Then the ground state I argued is all filled up. So you fill all the negative energy states, like that. And then to make the thing neutral, just by symmetry, you should fill half of the zero energy states. And then we'd argue that even with a really, really weak interaction, well, actually that interaction should be repulsive, it's just not any interaction, So a really, really weak, even a really weak repulsive interaction will preferably fill one of the SU2 flavor states, or SU2 isospin states, preferably, and not the other one. And that will appear like a sort of dynamical symmetry breaking with some tiny gap being formed. This will go down, that'll go up. Zero will be in between. And the bosons don't really matter for this argument because they get excited up here somewhere. Right, so this is an incompressible state in the condensed matter language. Incompressible just means gapped. To make a charged excitation, you have to push a charged particle across a gap. You don't have enough energy yet to excite a bosonic field, and so this is charge gapped. Okay, and then we interpreted that as symmetry breaking, so you get a psi-bar-psi condensate. The spectrum really looks like this. Well, in a magnetic field, these would be Landau levels split up again somehow, and that was the idea. Right? Now, what about if I put more charge into this system? Right, so here I have my magnetic field and I have a charge density. In this picture, it means I should start filling this next level, I guess. In this ultra-weak coupling picture, I start filling this guy up. And filling that guy up, okay, as soon as I start filling him, of course, I don't have a charge gap anymore because it's a highly degenerate state, right? I could move charges around here, so that looks like it isn't gapped. In other words, I could add more charge without adding much energy. There's no charge gap. So I should have a kind of an ungapped phase, but then when this is completely full, I should have a gap again. Well, it depends a little bit. It depends on maybe the splitting is enough that I cross the bosonic level, and then I could just keep adding charges that are bosons, and the Pauli principle doesn't apply anymore. And okay, it would never be incompressible again. Or if it isn't above the bosonic level, I'd expect another incompressible state. I have the slight problem over here that if I have charge density at all, it looks like I will never get another incompressible state. Right? Simply the argument that the lines of electric flux have to go somewhere, then the only place they can go is a horizon. Basically finishes off the possibility of ever seeing another incompressible state at sort of finite charge density. This problem is maybe even more severe if I have a lot of D branes, because I should have multiple copies of these levels. Right? So if I have a bunch of flavors, I really say I have N5 D branes. So then in a sense I have two isospin states for each of them. So I have two N5 towers of Landau levels here. And I can think of filling one and then another and then another. And the quantum Hall ferromagnetism argument, the weak coupling one, should really split up all of those. So I'd expect a whole bunch of incompressible states. And then the question again is, well, maybe the energy was split so much it competes with the bosons, but I can kind of control the splitting because it should be controlled by the interactions, not the magnetic field. So couldn't I make it small enough that, in this ideal system at zero temperature, you would actually see these, at least at weak coupling. And then at strong coupling, well, I don't know. So there's a question, is this telling me I will never see them again? Or is there another possibility? And the interesting thing here is that there's another possibility. There's actually a way out of this. Okay, and that I will get to after I talk about this system a little bit. So I need to introduce a few formulas now. So this was all sort of a qualitative argument. Let me now describe how you get some of these results at a more technical level. So the mathematical problem here is to find the geometry of the D5 brane. It's a probe brane, so it doesn't back react on the ADS5 cross S5 geometry, so that's all fixed. We're in a limit where the string theory is semi-classical, or actually just classical. So the mathematical problem here is to simply find the embedding of the D5 brane with the appropriate boundary conditions. So here the boundary conditions are that it comes to infinity, the boundary of ADS5 in a certain way. To find the geometry of the D5 brane, one has to extremize something called the Born-Infeld action. So the Born-Infeld action is the effective action for open strings at the disk level. Right? So if you have open strings that are ending on a D5 brane, the disk amplitude for those open strings, if you calculate it somehow, is supposed to turn into the Born-Infeld action, which is a function of the geometry of the D brane on which the strings are ending. That sounds like a tall order, but actually in the simpler case where the geometry is flat, but there's a gauge field excited on the D5 brane, a world volume gauge field, well, if the gauge field is a constant, I guess, it can't have much structure or it gets uncalculable. But if it's a constant, there's a classic old calculation due to Franken and Seitlin, which basically solves for the effective action you get by integrating out the open strings, and you get a Born-Infeld action with the gauge field included. Born-Infeld action just for the flat brane. And then early in the days of D-braneology, I'd say early 1990s, there's a nice paper by Rob Lee and one by Rob Lee and Joe Polchinski, where they actually generalize that to curved branes. I don't remember exactly how far they got. I think the curvature was weak, but they basically showed that the Born-Infeld action is the correct effective action. So we can take into account all of the dynamics of the string theory we need by just writing down a Born-Infeld action for our embedded D brane. So let me do that a little bit here. Sometimes it's called Dirac Born-Infeld action because I think it was also used by Dirac for something. And actually I don't remember why Born and Infeld like this action. Maybe somebody here knows. Dirac liked it because I think it made the energy of his magnetic monopole finite. But I don't remember what Born-Infeld liked about it. Okay, so the action for the D5 brane. Something like this. There's something called the D5 brane tension, which was also computed in a famous paper by Joe Polchinski a long time ago, and you can read in his book somewhere. Divided by the string coupling. So this does come from a disk amplitude. So 1 over G string is the appropriate power of the string coupling. An integral over the world volume of the D5 brane, which is 6-dimensional. Then here's the Born-Infeld action. I'm writing it with signs relevant to Minkowski space. So that's why minus determinant, because it's a metric here. And the determinant of the metric with Minkowski is, with Lorentzian signature, is negative. In here should be the internal metric or induced metric, or the metric that's induced by the embedding of the D5 brane, and then plus 2 pi alpha prime times the antisymmetric field strength tensor of the world volume gauge fields. And then that's not all in the action. So this is the part that's called Dirac-Born-Infeld. But there's other stuff. In principle, there's stuff that comes from the Chern-Simons term. It will not play a role yet for us, but I might as well write it for completeness. I think I called it omega 4, but I seem to call it C4 when I talk about probe branes. I called it omega 4 back when we were talking about D3 branes, but I think C4 might be, so this is the 4 form, Ramond 4 form, the classical one, the one that's part of the classical ADS5 cross S5 solution, sort of pulled back to the volume of the world volume of the D5 brane, and then hatted with these world volume gauge fields. And remember, the C4 has components that are in the ADS5, and then itself dual. It has another part that's in the S5 that's like the Hodge dual of the part that's in the ADS5. So if this world volume is going to be like ADS4, this would have to be the one from ADS5, and this flux would have to live in this 2-sphere in order to make this non-zero. And so far we don't have flux in the 2-sphere, so this will not play a role for us. Right? But if we did have such flux, then this would have to be included. Okay, the brane tension. There's some general formula for D brane tension. And then is written like this. And then remember the identification of our ADS CFT duality, that the string tension and the Yang-Mills coupling. If we want to talk about Yang-Mills theory sometime later on, the field theory side is given like this. So ADS5 cross S5, the space in which we're embedding this brane. The ADS5 goes here, S5 here. Has a metric which looks like this. So it has this L squared in front, the radius of curvature, which I could call root lambda alpha prime. Right? That was what L squared came out to be. Then it has the metric of ADS, which has R squared times the metric of Minkowski space for the first of the 4 dimensions, then plus dr squared over r squared. So this stuff we wrote down last time and maybe the time before. We've been writing it for a while. And then there's the 5-sphere, and I'll choose a particular way to coordinatize the 5-sphere here, which goes along with the discussion from there. I will, I want to have it so there's an explicit 2-sphere, and the way I'll do it is I'll split S5 into two spheres fibered over an interval. So the metric looks something like this. This psi is the coordinate that parameterizes the interval. I think it goes from 0 to pi by 2, something like that. The 2-sphere that the brane will wrap is just this one. And then the 2-sphere that it doesn't wrap I'll write like this with tilde coordinates. And these you'll recognize as just polar coordinates of the two-sphere, and this altogether makes a 5-sphere metric, the unit 5-sphere. Deep psi squared, yes. And there's a plus here. And any other mistakes? So the thing I drew up there with the S2 sitting at the top is where sine psi equals 1. And this is the S2 that it's wrapping. So this is the metric of that S2 sitting up there. And these parameterize the downhill directions from the top. As you go away from the top, actually this S2 shrinks and the other one grows up. When you get to the equator over there, this one shrinks to 0 and this one becomes maximal. So that's how one should think about this. The D5 brane I want to embed in this geometry. Most of the embedding is easy. It's just determined by symmetry. So let me see, let me write it over. I'll leave the pictures. So the embedded metric I will just use for the D-brane coordinates some of the space-time coordinates, the ones that the D-brane wraps in particular. So there's t, x, and y, and then r, theta, and phi. So its metric will look something like this. It inherits this radius of curvature from the space it's embedded in. And then this, the 2 plus 1 dimensional Poincaré symmetry, means it has to have this part. So dz is 0, z isn't here. So it's embedded at some specific position in z. And that could be z equals 0. In fact, z equals constant will be a solution of the equations of motion for the embedding. So you could assume it from the beginning, but that actually should be a result. In a sense. Then it wraps the r direction as far as it will do that. And then the only variable, the thing that can vary, is going to be the position of this thing on the two-sphere. So this brane truncating will simply mean this becoming r-dependent. And as you come down in radius from up here to down here, this guy moves down and at the bottom of the brane shrinks to a point here at the equator. So that's the only thing that will be going on here in this sort of minimal violation of the symmetries. That means that psi becomes r-dependent. And so what that inherits from this metric is this deep psi, which I call deep psi by dr times dr. Which puts, with the dr squared term, something like this in this metric. And then there's plus sine squared psi of r times the two-sphere metric. Okay, so this leaves us with an ansatz for the metric where one function of r tells us everything. And with this ansatz, what we want to do is extremize the Born-Infeld action. Whoops, not quite done. So this is the geometry of the brane, but there are also gauge fields living on the brane. I should make some ansatz for them. I want to turn on a magnetic field, and I want to turn on an electric field on the brane, which will correspond to a charge density at the end of the day. So my ansatz for the world volume 2 form field tensor looks something like this. It's useful to extract some, to define things with some constants extracted, basically to make this stuff compete with the curvature thing in front of the metric. There's an electric field, which I'll write in a particular gauge. The gauge is where the radial component, the R component of the gauge field is 0. So this is actually the time component divided by R. And this is the RT component of the 2 form. And so that will give the electric field on the brane world volume. And this A of R is a density, which will be dual to charge density on the boundary, in other words, the charge density in the dual theory. And then there's a magnetic field that looks like that. Okay. So this is what F is made out of. So there's B is like a modulus. Constant B solves, I don't know, Maxwell's equations in the bulk, or the Borden-Infeld equations in the bulk. So it's just something we could turn on. This will have an equation of motion which we will have to solve. Okay, so this is another unknown function. So actually there are 2 unknown things here, psi of R and A of R. Okay. B turns out to be a constant. That's good enough to make a constant magnetic field at infinity. Okay. So take all that stuff and plug it into Dirac-Born-Infeld, and you get some nice little action that looks like this. There's a bunch of constants in front. That come from integrating over the 2-sphere and integrating over the 2 + 1 dimensional space that nothing depends on, so you get a volume of it. Number of D5 branes, number of original D3 branes, root of lambda, which comes just from the curvature. And then we get the important part. Like that. So these are the R-dependent functions sitting inside this square root. And that's the thing that you're supposed to find an extremum of. So this is like kind of like a simple mechanical system. Right? You have a Lagrangian, and you have some generalized coordinate, right, which appears here, it is derivative here, and then this other degree of freedom, which is also like a generalized coordinate. And actually, the action depends only on its derivative. Right? Only on the velocity of that generalized coordinate. And whenever that happens, if you... the sign, S-I-N. Sign. Well, this one, A of R. Okay. Unfortunately, not this one. That would be really good. But this one already simplifies things. Okay, if it depends only on the velocity, then it's what's called a cyclic coordinate. And you can, its equation of motion gives you a conservation law, and you can sort of eliminate it in terms of a conserved quantity. And here that conserved quantity will be the charge density, actually. So it does something nice for us. So we can observe right away that A of R is cyclic. So cyclic variable obeys that equation, Euler-Lagrange equation, and that means that the functional derivative by this velocity of the action is equal to a constant, which I'll call Q5, and probably in what I've done here, there's some numbers in front of Q5 to give it a better, more workable definition. All right, coming from the stuff in front, all this junk in front. Okay, so this is an equation which is a derivative of this thing by A prime is equal to a constant. That equation can be used to eliminate A prime. Right, you can take and solve that for A prime in terms of the constant and the rest of the stuff, plug it back in and eliminate A prime. And that's almost the right thing to do. There's one other thing that you should do when you do that, and that's a Legendre transform with respect to A prime in order to get what's called the Ratheon. Right, that would be then the correct thing to vary, because here you're supposed to vary this psi, keeping A fixed and A prime. Whereas once you eliminate A in terms of this constant, you would rather vary psi keeping that constant fixed rather than A. And you need a slightly different functional for that, which is a Legendre transform of this one. What's the question?
This expression Q5 and the next curve.
Oh, some constants, which I would write if I knew what they were, but I think it's actually just this junk in front. Oh. Q5 up to a constant. I want to define Q5 in a way that's convenient, that isn't going to make me carry around a whole bunch of constants through my Legendre transform. Is to do the Legendre transform, I need it to be nice. So I think I need to factor out all this stuff in order to make it nice. Right? So some constants. And actually it's Q5 times all the constants. Well, not quite, because this also wasn't quite canonically normalized because of his definition here. So it's Q5 times some constants that is the charge density. In a sense, the dual to this gauge field. And you have to figure out what they are. You can't get away with just throwing away these constants. It will be important what they are, but I will not write them for you now, because there's enough writing as it is. Okay, so what I want is actually the Ratheon, which is something like S minus the integral of A prime of R. This Legendre transform of the action. And let me call it for the 5 brane, because there's many actions hanging around. And so that comes out equal to all these terrible constants. Lambda n 5, 2 plus 1 dimensional volume, 2 pi cubed, And then something with a big square root. It's halfway to the Hamiltonian. You've done the Legendre transform to get to the Hamiltonian, but for only one of the 2 degrees of freedom. Okay. That's precisely what Ratheon is. And I don't know actually any more than that. That's all I remember from Goldstein's book when I was an undergraduate student. I don't know, Goldstein's book might now be really ancient. I don't know if you use it anymore when you study mechanics, but the magnetic field appears here, and the charge appears here under the square root, and then this is multiplied by this other thing, but now with the A prime gone. And so one should extremize this to find this function psi of r, with the boundary condition that as you come up to the top here, this 2-sphere should return to the North Pole. And the embedding should be otherwise smooth, which means when psi comes down to 0, that's when the embedding would cap off. In some sense, it should be sensible. Right? Psi should come from pi by 2 down to 0. That's where the thing ends. So you can derive equations from this. I'm not going to do it because at some point this becomes a numerical problem. It doesn't look that hard, a simple mechanical problem, but still the approach that I know to it is numerical. Right? One simply takes Mathematica and finds the differential equation that psi satisfies and integrates it numerically, looks for solutions. And I've worked on this, and that's the way I did it. Actually, I use Maple instead of Mathematica because coming from Canada, we get Maple for free. But there's not a very big difference, but well, maybe there is. Actually, my Italian collaborators, they use Mathematica, and they do a better job of this integration a little bit. So maybe Mathematica somehow has differences in it that help. But just from looking at this, one can sort of see how the behavior happens. So if the magnetic field and the charge are switched off, the only extremum of this should be at psi equals pi by 2. And really, the equation wants to minimize this thing. And you can see making psi r dependent works against that. If psi is r dependent, it gets bigger, not smaller. So the first stuff should somehow compensate psi growing up. If B is switched off, it has an r to the 4th in front of it. The compensation would be most effective at small r. But with r to the 4th in front of it, this is rather ineffective at compensating anything. And actually, it doesn't do it. So psi equals a constant when these things are switched off is the only solution. As soon as you switch on B, without the Q, you completely change this thing at small r. In some sense, you change the effective dimension of the space down near the horizon. This no longer gets turned off as r goes to 0. It's still there. And then there's always a lower energy solution where psi gets small as you come down into the space. And so the R-dependent solution is always there in that case when just B is switched on. When you then switch on Q5, well, there's not a lot of difference, but it does make this switching a little less effective. So you might imagine as Q5 gets bigger, maybe the constant solution becomes competitive again. And that's exactly what happens. So here there's a phase diagram where if Q is switched off and B is turned on, you always have a gapped phase. Psi is always R dependent. As you turn on Q5, when it's small, you still have the R dependent phase. But when Q5 gets big enough, there's a critical value where actually psi is a constant becomes the only solution again. Okay, so I can draw a phase diagram. That looks something like this. So if this axis is B and this one is Q, it's a bit of an illusion, this phase diagram, because if you scale things, things only depend on the ratio of B and Q. But let me draw it that way anyway. So down here is the only charge gapped phase that we found. Sorry, it's not really there. This is B equals 0 and Q equals 0. This is B equals 0 and Q equals 0 is the conformally symmetric place. As soon as you switch on B, leaving Q equals 0, there's a charge gap. So it's gapped all the way along here and all the way along here. That gap goes away when you switch on Q. The charge gap goes away, but the symmetry breaking is still there. So in some sense, it's a picture that I had drawn over here where you're filling up energy states, but you have a Fermi surface. Right, so you have the massive phase, symmetry breaking phase, but you have a Fermi surface. And then at some critical value of Q, it just ends. And you no longer have the psi bar psi condensate. You no longer have symmetry breaking. In other words, this guy stays at the top of the sphere. And so beyond here, and it's Q proportional to B. So outside here, you have SO3 cross SO3 symmetry. Inside here, you have just SO3. The second SO3 is spontaneously broken. And then if you come back to the origin, all symmetries are good again. So a crude version of the phase diagram looks something like that. And this is known. This is not my work, finding this out. There was quite a bit of work on this sort of probe D5 brane and 2+1 dimensional system. The group around Nick Evans, I guess Nick Evans is in Southampton these days, or he's based in the UK somewhere. If you look back, their physics letters papers of a few years ago are probably the most advanced summary of this. So they also do this at finite temperature. So you can also restore the symmetry by temperature as well as density. So you can add temperature to the phase diagram, and you can trade off density for chemical potential. And then there's another phase transition called Maison Melting. And so it has a fairly rich phase structure. Okay. But like I said, there's no more, as long as you're at finite charge density, there's no more charge gap phase visible in the D-brane system. So weak coupling, we can find charge gap phases. We just have to make the coupling weak enough that we stay below the threshold for creating bosons. But at strong coupling, apparently there's no more. And I guess I kind of thought that was okay for various reasons. It shows you how you can convince yourself of something that's wrong if you try hard enough. I thought that was okay. Well, it's strong coupling. Landau levels are definitely single particle physics. Like even at weak coupling, they're mixed with each other. So it's strong coupling, maybe Landau levels make no sense at all, and so on. Things are mixed up, so maybe you never see any more of the ungapped states coming from filled up Landau levels. These are also called Hall states, by the way. They're just integer Hall effect states. Right? So that's a single particle phenomenon where you have gaps coming from completely filled Landau levels. So I had more or less convinced myself that there probably aren't any, and this system therefore maybe isn't very interesting if you want to study quantum Hall physics. It has only one integer Hall state, the one with zero filling fraction, actually, the charge neutral one, and that was it. But in fact, that's not the case. There's a whole bunch more solutions of this theory where there is a whole zoo of these gapped states. Probably they happen before this symmetry restoration, and so this phase diagram doesn't seem to be quite right. There's a whole bunch more structure in here, and I will tell you about it after we take a little break. Okay, so I've described the D5 brane and some aspects of doing holography with it. But there was sort of a nice realization in this subject that the D5 brane isn't the whole story. And in fact, one can find more states of this theory. And these states resemble a D7 brane. Now, the boundary conditions of the problem actually tell us that up here at the boundary of ADS5 space, the object you're embedding should look like a D5 brane. But there's nothing stopping us from thinking of the object down here in the bulk as being something else. And the most natural something else is a D7 brane, which as you come up here pinches down to a D5 brane as you come to the surface. That D7 brane would have, well, similar symmetries to the D5 brane. Its main difference is it would have a second sphere here, which it would wrap. So it wraps two of the two spheres sitting inside S5 instead of just one of them. And the way it pinches off when it comes up to the boundary to become a D5 brane is this second sphere pinches off to a point. So that's what allows it to have a smooth limit there, in that it has a shrinking cycle. And that limit is a D5 brane, so it would have the D5 brane boundary conditions. In the bulk, you could think of it as a blow-up of a bunch of D5 branes, if you like. I'm not 100% sure you should think of it as a blow-up, but you could as a blow-up of a D5 branes using the Myers effect. So if you're familiar at all with the Myers effect, and even if not, what happens with it is in certain extra fields, the Chern-Simons terms in the type 2b string theory action tend to make D-branes look of one dimension look like D-branes of another dimension. And typically this is a bunch of D-branes of the lower dimension kind of blowing up into a fuzzy object in the higher dimensions. And that's driven by background fields. That can happen here because if you write the D7 brane action, it looks something like this. So there's a D7 brane tension divided by G string, as usual. It has an 8-dimensional world volume. Inside here, again, is Born-Infeld. And then the Chern-Simons terms add something like this. This C4, which now could be integrated on either the 5-sphere side or the ADS side of the embedding. And that's because we could have these F fields on the ADS side. So this could be the C4 for the 5-sphere in ADS 5, cross S5. And these could be the 4-form you could make out of world volume gauge fields on the ADS part of the D7 brane. And so the idea is, for this problem here, we would study a D7 brane whose world volume is roughly ADS4, at least asymptotically, cross S2, cross S2. These two S2s sitting inside the 5-sphere. And then this disguises, this is really disguises itself as a D5 brane when it comes up to the surface by one of these S2s shrinking away and becoming the D5 brane we were talking about before. Okay, so this all looks very reasonable. The thing that might blow up this D5 brane into D7 brane is if these gauge fields are actually excited. So these could be the B field and the E field we were talking about before. This is C4 in the 5-sphere, so now this term would play a role and it would add something to the energy. And just maybe it would lower the energy of the D7 brane enough that it would compete with the D5 brane. So that's the idea here. That now Chern-Simons is going to be important, and maybe it does something for us. And then, of course, it's fairly obvious what to do. Make the ansatz for the D7 brane metric, plug it into the Born-Infeld action, and look for solutions with the appropriate boundary conditions. Calculate the on-shell action and see if it competes with the D5 brane, where you do the same thing. Okay, so there's lots of calculation to do and lots of numerics, but conceptually it's pretty straightforward. Does this solution compete or does it not compete with the D5 brane version? Okay, so that one can do. Just let me try and describe in words what this would do for us. It actually does something kind of interesting. The action for gauge fields here, if we think of gauge fields, well, remember what we were doing here, we were turning on an electric field and a magnetic field in the brane world volume and sort of studying what happens as we change the magnitudes of those. Right? The electric field gave us charge density and the holographic dual to this, and the magnetic field was just magnetic field. So here we turn on an electric and magnetic field and you get this kind of axion term in the action. FF dual times this C4, which is something integrated over this sphere, which will turn out to depend on the radius. So C4 kind of plays the role of an axion here. And we can see in more detail what it does, but you'd think of it as something R dependent. In fact, what it will do is it will go to 0 at the boundary, where this should become a D5 brane, and this stuff would be absent, and it will become something inside. Its variation is actually quantized by the quantization condition for C4, In the extreme case where the brain wants to pinch off, C4 goes to some constant inside, which is sort of given. One has to work through the numbers to see what that constant is, but it's sort of quantized as a constant. So inside the brain world volume, instead of just this Born-Infeld electrodynamics that we had for the 5 brain, we have a kind of an axionic electrodynamics where you add this FF dual term with something R dependent in front of it. What does that do for us? Well, this kind of axion term, what it would do to Maxwell equations, for instance, is kind of mix what you mean by E and B. In a sense, it gives terms which mix E and B. If you think of Maxwell's equations, electric and magnetic field. What it can do is replace electric field by magnetic field, therefore, and vice versa. So what could it do for us here? Well, maybe if things were just balanced, there'd be another possibility to these electric field lines having to go all the way down here through the horizon. Maybe they could end by just dissolving into magnetic field. Right? They could, as you come down here, be converted from electric field lines into magnetic field and basically go away, and then this brain would be free to truncate again. So that's the idea. Now, how much electric field could be dissolved that way? Well, it depends on the constants here. So one has to figure that out. How much electric field there is, of course, that's what determines the charge density and the magnetic field here. So one can go through this simple exercise. Well, the not so simple exercise if you don't like keeping track of all the constants, but anyway, it's certainly possible to do it, to figure out how much charge density versus magnetic field you would have to have in order for this mechanism to work. It turns out that the answer is that charge density is exactly the one that would fill up another Landau level on the field theory side. This is 5-dimensional, but remember in the dual field theory, in the field theory side, these things are charge density and magnetic field. And you get completely filled Landau levels when suitably normalized charge density to magnetic field is given by some discrete number.
We got Landau levels because the theory was especially 2-dimensional.
That's right. That's on that side.
Yeah, but now
This side it's 4-dimensional, right? Right? The brain, the ADS4 side of the brain is 4-dimensional. So we're solving equations here, but there is a field theory dual to what's going on here.
yeah, but the dual is 3-dimensional.
2 plus 1-dimensional.
Even for this
Yeah. It's the same theory. The dual is a deformation of the same theory, and that's because what the dual theory is, we take from the boundary condition here, that this is just a D5 brain up here.
But the dual theory was not coming from the intersection between the D5 and D3 brains.
Well, in a sense it is, yes.
So now we have an intersection between D7 and D3 brains.
Well, you still think of the D7, you could think of the D7 as just a pile of D5 brains that blows up to this fuzzy D7 brain. So you have to think of it as just another state of the D3, D5 system. Okay. There's one thing I forgot to say. When this becomes a D7 brain, it actually records the number of D5 brains. And the way that it records it here is that this second sphere that blows up, it has a Dirac monopole bundle of U1 magnetic flux in it. And the number of units of magnetic flux is equal to the number of D5 brains. So that's how this theory remembers that it came from some D5 branes. Right? And so in some sense, a bunch of D5 branes have dissolved into a D7 brane. But to get the flux right, the Raman-Raman flux right, you need this magnetic flux here. So I think what you do is you take the Raman-Raman D7 brane flux, exterior product with this flux, and take the Hodge dual, and that should be D5 brane flux if the dimensions come out right, and if I'm remembering it correctly. Okay, so in some sense it has to maintain D5 brane charge, and that's how it does it, by having this extra flux on its world volume. Okay, so the idea here is one, well, has some competing states. So we have to write down what the theory is. So one can make the same ansatz for the metric now. Let's see, maybe I should. Which is similar to the one I did for the D5 brane, so maybe I won't write it again, except it also wraps a second two-sphere. So it wraps both of the two spheres. So its symmetry breaking is a little bit different somehow. Right? It will still be SO3 cross SO3 symmetric. So the symmetry breaking scheme is just different. The one thing to know is the C4, how it appears. So to reproduce all those formulas, the main additional thing is this 4 form. So in the coordinates we're using, it looks something like this. This is the one on ADS4, on ADS5, sorry, and then the part on the 5 sphere in terms of these 2 sphere coordinates. Is just this. Where C of psi is something which gives you sine to the 4th psi, I think it's sine, well, some powers of sine psi, when you take its differential. Such a d of this thing is the constant 5 form flux. I think there's a 4 here, but in my notes I don't have the 4. I think d of this should produce cos squared times sine squared psi somehow, and it won't do it unless with just a sine psi. Okay, so this is C4. The embedded metric is very similar to what we wrote down before. You just add the extra 2 sphere part. The F is identical to what we had before. Right, it has a magnetic field, the electric field in it. And so you have all the ingredients to construct the action, and it looks a lot like what we had before, just a little more complicated because now it's for D7 brane and it has this extra term in it. But the features are the same. The main dynamical things in it, the things that have to be determined, are these two fields. Right, this is the world volume gauge field, and this is the latitude at which these spheres sit. This is again a cyclic variable that can be eliminated. So all of the arguments are the same. And you come down to a Ratheon, which looks somewhat similar to what we had, and which I will write for you maybe here. So the Ratheon for the 7 brane has these same numbers in front of it, except it doesn't have N5. Now it has a big square root under here. And underneath the square root there's also a charge squared term. That looks like this. And then this is multiplied by this same old kinetic term for psi. So it looks like that. The D5 brane was similar to this, same coefficient with all of this first square root. I'll just remind you what it looked like, replaced by this stuff. And I'm doing this so I brought this parameter f into here. So that one could compare them better. So it looked like this. So the differences between the two are just in this square root. So remember we had an argument when Q is switched on, eventually this becomes ineffective. When B is switched on down near r equals 0, it has a huge effect because it replaces r to the 4th with a constant. It's like changing the dimension of the space down there if you think of this as a Jacobian for polar coordinates. Up here it's a similar story, except there's this extra part from the blown up 2 sphere. It doesn't really do much. Here F is, well, it's a magnetic flux through that blown up 2 sphere. Down here that's just a constant. I've kind of put it in here so this blow up part doesn't do much. This is fairly innocuous. This does the same thing. This is what really does the whole thing. So this is the charge, but then you have 2 times the magnetic field times this C function here. And the C function depends on radius. At infinity, psi goes to 2 pi, or sorry, to pi by 2, so this C function is 0. And then as you come down from infinity, psi grows up, presumably, if it's, or comes, I should say psi comes down from pi by 2, but this becomes negative, I guess, the way it's written. And eventually when psi goes to 0, it comes to minus pi by 2. So this C varies with r and comes to something non-zero. If this Q and B are just in the right ratio, C can make this final term vanish for small r, and it can go away. So it can overcome the effect of Q squared in here. And that's what allows you to have a gapped solution again, where psi will cap off, in fact. When Q is non-zero. Okay, so that basically is how this mechanism works. But then you have the Ratheons there. You have probably numerical solutions, so all you have to do is compare the two solutions. Right? One had solutions of the D5 brane system with some Q and B. Take the D7 brane, find solutions with the same Q and B, plug them in and calculate the Ratheons and see which one has lower energy. And indeed, the D7 brane does pretty well in this competition. In fact, even before it gets to this magic filling fraction, where a gap can happen, the D7 brane actually becomes the preferred state. So one has a picture of a phase diagram that looks something like this. Actually, let me call this here then filling fraction, which is the charge density, which I'll call Q, although it's a different normalization from this Q, divided by how much charge density fits in a full Landau level. And that's B over 2 pi, the number of flux quanta in the Landau level. There's some other normalizations here which I won't worry about, but this I call the filling fraction. And in the integer quantum Hall effect, it's when this ratio is integers, is when you have your incompressible Hall states, the ones with the charge gap. So we had a charge gap state at 0. If a magnetic field is turned on, that means there was no charge density. So that was the original state. Then we introduced a charge density. Down here, the favorable states are D5 branes. Eventually, one should get to where in the actual system you might expect a gap, where this ratio is 1. What happens is somewhere in between. I think it's about a third of the way. It's not even half. The D7 branes actually become energetically favorable. When you get up to here, the D7 branes, by this mechanism we talked about, can get a charge gap. So they can have a solution that pinches off before it comes to the horizon. And so this is a gap state. And so here in this, on this phase diagram, you have the nu equals 1 integer quantum Hall state. Now you don't have a quantum Hall plateau in this business because you don't have all of the other physics of the quantum Hall effect. The quantum Hall effect depends on localization physics and things like that in order to make a plateau. So here, the incompressible Hall state is actually only at 1 point, not at a plateau, but indeed we find it. Then what happens if you continue increasing the charge density? It turns out that the energetically favorable state seems to be one where the charge density to get this far actually still stays in the gap D7 brane. If there's more than one brane, a bunch of branes, there will here be ungapped D5 branes. So there'll be one D7 brane that kind of absorbs a quantum of charge and remains gapped. And you come back to a bunch of D5 branes which are ungapped. And then at some point here, which is even smaller, so this is a D7 gap D7 D5 composite system. At some point here, these like to switch over to a bunch of D7s. A gapped D7 and a bunch of ungapped ones. The gapped one absorbs the sort of quantum of charge, and then the rest of the charge, which doesn't fill a Landau level, has some ungapped ones. And when you come up here, the solution is just two gapped D7 branes. So you get another one like that. And then between 2 and 3, the D5 branes don't seem to come back at all. Of course, this is numerical calculation, so you can't say for sure that somewhere really close here there isn't a solution with D5 branes. But here what you have is 2 gapped D7s and ungapped D7. Absorbing the rest of the charge. And then the story just continues. At 3 you have the other D7 gaps, and you have 3 gapped D7 branes, and so on. Now these D7 branes are made out of D5 branes, and those are finite in number. They might be large, but finite. They give a number of flavors. And so the maximum number of D7 branes you could gap is equal to the number of flavors, actually. So there's an end to this chain when you get to N5, the number of D5 branes. That's the maximum you could get. And in the numerical calculations, N5 was actually fairly big, and that's because this number F in here is N5 divided by root lambda. There might be another parameter with it. Yeah, it's 2 pi NF over root lambda, N5 over root lambda. And the numerics works best when this F is of order 1. Although I have checked that these solutions exist down to where it's 1 over 100, like 0.01. But there it becomes not very stable, not very reliable. So it works best when F is of order 1. And that means this is really working with the number of D5 branes is pretty large. But this has only been tested out to something like 5 repetitions. So one doesn't know if it really goes on to N5. That's just a theoretical limit of how many states you have. Okay, so on the field theory side of this, at weak coupling, what does this look like? Well, it really looks like these N5 actually 2 N5 towers of states are getting filled. So all the negative energy states are filled, so everything below some level is all filled up. And then you start with, say, the neutral state, which is half filled. So let me just make NF equals 2 for the sake of finiteness of my ability to draw. So you start and say this is a 0 state, so you start with them half filled. Right? And then you start filling, so you start putting stuff in here. That doesn't have a gap. And then when this is completely filled, that gets gapped. And then you start here, and you expect 2 more gap states. So you expect exactly N5 gapped ones, the same as the number of D branes. So that counting actually works. Right? Here you can have at most N5 D7 branes. And to have N5 D7 branes means an individual D5 brane is being replaced by a D7 brane. So that really isn't really a blow-up in the usual sense. Right? The Myers effect always has a large number of small branes blowing up to look like a bigger brane. It's like making a fuzzy sphere out of D0 branes. You really need a lot of them to more or less color the whole sphere. So it's not clear that Myers effect is really the right way to think about this. Could be just thinking about it as competing solutions of the same problem is better. But in any case, the counting comes out beautifully. And so one has a whole bunch of incompressible states, which are integer quantum Hall states. There are symmetry breaking patterns and things one could do with these. And as I told you last time, I won't repeat the arguments. This kind of quantum Hall ferromagnetism, this sort of breaking up of the flavor symmetry in this environment, is actually seen in some Dirac semimetals like graphene. And those semimetals tend to be strongly interacting systems. So that means that this holographic approach, I think, is the only way to see this stuff in a strongly interacting system. So at least qualitatively, we have something to offer them. The statement is that their weak coupling arguments actually survive in a strongly coupled system, which is the system, which is what they have. They have a strongly coupled system where they're seeing the phenomenon. So at least we have something qualitative to tell them. Okay, so that's the D7 story. And I do have a few minutes left. So let me give a teaser for what I will do tomorrow in the grand finale. So tomorrow I would like to go back to defect conformal field theory and talk about it a little bit, because from a formal field theoretical point of view, this probe brain system also has some interesting aspects. N equals 4 conformal field theory you might be somewhat familiar with. The statements of conformal field theory, they're there in N equals 4. In fact, there's a huge industry called the integrability program, which is centered around calculating the conformal dimensions of various operators, or huge classes of operators at the same time even. So the N equals 4 conformal field theory is a well-developed subject, which a lot of people work on. The theory, when you introduce this defect, is a little bit less well-developed and has some new aspects to it. It still has a conformal symmetry, but it has a defect sitting there. So it has more variables in a sense. So for example, if we picture it like this diagram I've been writing here. Four-dimensional space-time, three-dimensional defect. If you have a point here, its position is some distance from the defect. So this just geometrically gives something extra that correlation functions can depend on. That complicates a bunch of things. So for example, if you have a two-point function of scaling operators, the 2 points are somewhere in this space. Each of them is some distance from the defect. So there are a bunch of things it can depend on. It's no longer rotationally invariant. It can depend on the position sort of in the directions parallel to the defect as well as the distance away. So 2-point functions already, you might think, get complicated. And so it might not be such a beautiful subject after all. It's complicated immediately. There is one part of it that is nice, and that's that you can have 1-point functions. The existence of a 1-point function is no longer forbidden by conformal symmetry. Why would it be forbidden before? Well, it would have to have dimension 0 in order to have a non-zero expectation value. Right? Your operator, and there can't be operators of dimension 0 because there's a lower bound on conformal dimensions of operators coming from unitarity. So there are no 1-point functions in an ordinary CFT, but in a defect CFT there could be. If this distance from the defect to the point x is z, this can go like 1 over z to the power of the conformal dimension of the operator. And so there are a bunch of things that are there in defect theory that aren't there in just an ordinary CFT. And these are things that one might think about computing. And next time I will show you a computation of one-point functions in this very theory we've been talking about. Well, not quite, in a slight deformation of this theory. Slight modification I'll tell you about later. In the modification, though, I will be able to compute this in weak coupling and in strong coupling, and I'll actually be able to extrapolate across the gap to check if a prediction for certain one-point functions actually agrees when you calculate it on the gravity side of ADS-CFT. And this, I believe, is quite an interesting subject. It's why I include it here, because it's something where there's actually interesting things to work on. And with that for today, I'll conclude. See you tomorrow.